Hey guys, welcome back. In this video, I'll be talking about triple integrals over general regions in space. These are known as type 1, type 2, and type 3 regions. Actually, these regions are very similar to each other. Anyway, let me start with the definition of a type 1 region. Right, a solid region E is of type 1 if it lies between the graphs or surfaces of two continuous functions of x and y. In other words, it consists of points x, y, z such that x, y comes from a region D on the xy plane, whereas the variable z is bounded by two functions of x and y. So here we have u1 of xy in the lower bound and u2 of xy in the upper bound. Also, the region D is known as the projection of the solid E onto the xy plane. Here's how we can visualize a type 1 region in space. So suppose the blue region here is the type 1 solid E. And suppose we put our eyes and view the solid from the positive z-axis. So imagine we have rays of light coming down from the positive z-axis. Then the shadow that we see on the xy plane of this solid will be the region D, which is the projection of the solid onto the xy plane. And now the definition says, for any point that we choose from this region D, let's say this point here, given by x, y, then the region E must consist of all the points vertically above this point xy, starting from the lower surface and all the way to the upper surface. So basically this vertical arrow above the point xy, starting from the lower surface given by z equals u1, all the way to the top surface, z equals u2, will be entirely inside the region E. And now if we do this for every point inside D, then we'll get a collection of vertical arrows whose initial points lie on the lower surface and the terminal points lies on the upper surface. And hence the type 1 region is the region consisting of all these vertical arrows. Do you follow me? Alright, let us see now how we can compute a triple integral over such a type 1 region. Well, basically, this will be given by a double integral over the projection D, followed by the most inner integral with respect to the variable z, from the lower bound to the upper bound. In other words, the inner integral, or rather the most inner integral, is a single integral with respect to z by holding x and y fixed. So this will be the integral computed along these blue vertical arrows. Do you see that? So for any fixed x and y, the inner integral is computed along this blue vertical arrow. So after computing the inner integral with respect to z, the resulting function is just a function of x and y. In other words, z will disappear after we evaluate the inner integral. And suppose the resulting function is some function g of xy. And then we'll have a double integral of this function over the projection D. Well, this makes sense because D is a region on the xy plane and the integrand is some function of x and y. Okay. Depending on how we describe the region D, this can be further evaluated by turning it into a sequence of iterated integrals. But we already know how to do that from previous study. Alright, let us now look at type 2 region. Well, a solid E is of type 2 if it lies between the graphs or surfaces of two continuous functions of y and z. So this time, the solid E consists of points such that YZ comes from a region D on the YZ plane, whereas the variable X is bounded between two functions of Y and Z. And here the lower bound is given by U1 of YZ and the upper bound by U2 of YZ. As before, this region D is known as the projection of the solid E, this time onto the YZ plane. And here's how we can visualize a type 2 solid. Now suppose we put our eyes here at the positive x-axis, and imagine they were rays of light parallel to the x-axis, as it were, going towards the solid E. Then the shadow that we see on the YZ plane will be the projection D of the solid E. Okay? And furthermore, for any point YZ coming from the projection D, there will be a corresponding arrow starting from the surface x equals U1 of YZ, going in the positive direction of x until it reaches the surface x equals U2 of YZ. And if we do this for every point in the projection, we are going to get a collection of arrows that look something like this, whose initial points lie on the surface x equals U1 of YZ, which we'll call the back surface of the region E, and whose terminal points lie on the surface x equals U2 of YZ, which we shall call the front surface bounding the solid E. Do you follow me? So the region E consists of all these horizontal arrows going from the back surface to the front surface. Alright? And this is how we are going to compute a double integral over a type 2 region. Well, basically we convert this into a double integral over the projection followed by the inner integral with respect to x from the lower bound U1 of YZ to the upper bound U2 of YZ. And after evaluating the inner integral, the variable x will disappear, and the resulting function will be some function of y and z, let's say denoted here by g of yz. Now this makes sense because next we're going to compute a double integral of this function over a region D which lies on the YZ plane. Okay? Let us now move on to a type 3 region. Well, a solid E is of type 3 if it lies between the graphs of two continuous functions of x and z. So this time, the solid E consists of points such that xz comes from a region D on the xz plane, whereas the variable y is bounded by two functions of x and z, given here by u1 in the lower bound and u2 in the upper bound. Again, the region D is known as the projection of the solid E. Here's how we can visualize a type 3 region. Suppose we put our eyes at the positive y-axis and imagine they are rays of light parallel to the y-axis going towards the solid E. Then the shadow of the solid on the xz plane will be the projection D of the solid. Okay? And furthermore, for every point xz on the region D, there will be a corresponding arrow starting from the surface y equals u1 of xz, going in the positive direction of y until it reaches the surface y equals u2 of xz. And if we do this for every point in the projection, we're going to get a bunch of arrows, or rather horizontal arrows that look something like this, whose initial points lie on the surface on the left, given by y equals u1. So let's call this the left surface, and whose terminal points lie on the surface y equals u2, called the right surface, bounding the solid E. And hence, the region E consists of all these horizontal arrows, which are entirely inside this region, starting from the left-hand surface all the way to the right-hand surface. Now, here's how we can compute a triple integral over a type 3 region. Basically, we convert this into a double integral over the projection, followed by a single integral with respect to the variable y, from the left-hand surface to the right-hand surface. Now, after evaluating the inner integral, the variable y will disappear, resulting in a function of x and z only. And let's suppose this function is given by g of xz. Then the double integral makes sense because it's a double integral of some function of xz over a region D which is on the xz plane. And so the final answer will be given by this double integral over the region D. Okay guys, in the next video we're going to see some examples. Stay tuned.